send your video with your presentation to other participants who were invited, but due to some reasons could not come, and then they could watch your presentation at any time they want. Okay, so we start our seminar. Our speaker today is Dr. Shan Wang. She is from Center for Marine Technology and Ocean Engineering in Lisbon. Shan, if you want to introduce yourself in more details, please do this. Like where you've been, what you did, and what you are doing now, just as an introduction. Okay, and please start your presentation and your introduction if you want. And then, and now I'm switching off my camera and also my microphone.
Okay.
Okay.
Thank
Please
you for your introduction, and thank you for your invitation for me to speak in this seminar. And I'm Shan Wang from Center of Marine Technology and Ocean Engineering, University of Lisbon. So I did my PhD in University of Lisbon regarding SLAM-induced response and SLAM load prediction on ship structures. And my research interest is focused on ship vibration, ship slamming, and mooring analysis for floating production system. Now I am the assistant professor in the university. So next I will start my presentation regarding analytical solutions for ship slamming. In this presentation, first I would like to give an introduction to slamming problems and then make a review on slamming load analytical models, which will be followed by several practical applications of these models and some results comparing to experiments and numerical solutions. At the end of the presentation, there will be some general comments and discussions. The wave impact caused by slamming can be roughly divided into 4 types. This is the bottom slamming. It happens when the ship emerges and re-enter into water surface. This is the bone flat slamming. It occurs to high relative speed of the bone flat to the water surface. This is the breaking wave impact for offshore structures. The breaking wave impact happens also for ships, and it is generated by the superposition of the incident waves and bound wave hitting the bow of a flat ship, even for very small ship motions. The last is green water impact. So in our study, we have been focused on the bottom slamming and bone flat slamming. When a ship is advancing in rough seas, the ship hull may impact with the wave surface due to very large vertical motions. During and immediately after the slamming, there is a period of localized responses when the hull plate will respond immediately. The impulsive pressure load induced by slamming can lead to damage on the hull of marine structures and affect the structure response globally. Slamming introduces also whipping response. The whipping response refers to the hull gather vibration due to slamming. The local slamming is also likely to happen on the wet deck connecting 2 hulls of a catamaran. Looking at these 2 pictures, we can see we have different geometries on this connecting plate. This is a wedge shape plate, and here is a very flat plate with very high.
Shan, excuse me. On your slide, in the right bottom corner, there is the Yeah, just close it. Click on the cross. And yeah. Yes, perfect. Thank you very much. Thank you.
Okay. So look at these two pictures. We can see this is the wedge type geometry, and this is a relatively flat plate. For the flat plate, and when the ship is advancing in very high speed, the impact between the plate with the wave will induce very high slamming pressure, which will cause damage owing to even one single impact. The wave load response of a ship in harsh or extreme irregular waves and the structural safety is a special reason of concern, since ship operates in unknown, severe and high-risk environments. Marine accidents due to structural failure may occur at sea. There are some examples. The first example is the 275 meters long container ship, which was caught in stormy wave. And this example is for a 5-year-old container ship, which was broken into 2 segments in very severe weather. There are also some examples for the local ship damage due to wave impact. For example, here it is the Estonia ferry disaster. The disaster killed more than 800 people because the bow of the ship broke and the ship sank. So here is an example for Fpso. It is a floating production loading and offloading system. In the picture, we can see there is a very big permanent deformations due to repeatedly water impact on this location. So from these cases, we can see that the accurate assessment of slamming load and associated structural responses are very important in the design of marine structures and ship safety. The study regarding ship slamming consists of 3 aspects: the identification of the occurrence of a slamming event, the slamming load prediction, and also the hydroelasticity of ship. All these 3 aspects have not been fully understood because of the complexity of the problem. The common hydroelastic models for ship slamming commonly involve the 3 models: the structure model of the ship, a hydrodynamic model of the fluid, and a coupling method to enable the interaction between fluid and structure. The structure model is usually represented by a beam model or 3-dimensional finite element model, while for the coupling method, the model approach is the most common method. For some cases, the in-house developed or open source coupling interface have been developed to couple CFD solver with 3-dimensional finite element. While for the hydrodynamic model of the fluid, there are 2 approaches: the potential flow-based solution and the CFD tools. While for the potential flow-based solution, there are usually 2 approaches: the strip theory approach or the boundary element method. So theoretically, the coupled CFD solver with a 3-dimensional finite element model can simulate any situation of the fluid and can study most of the physical aspects of ship slamming. However, this fully coupled method is very difficult to be realized because it involves full models of the ship in both solvers, and it is very time-consuming. The numerical uncertainties on both solvers are difficult to be identified. And the accuracy of the result depends also on the experience of the users. On the other hand, the potential flow-based method is still widely used because they provide satisfactory results comparing to experiments. In 2018, the Dynamic Response Committee in ISSC Congress made a summary of the numerical whipping models based on potential flow hydrodynamics. And in this model here is the list of the C-clipping models, containing two-dimensional strip theory and three-dimensional boundary element method. This is the structure and capping model, the finite element method, the beam model, and the model approach, one-way and two-way coupling between the two solvers. Then if we look at here, it is the slamming model. From here, we can see that the analytical two-dimensional slamming models are widely used in the potential flow hydrodynamic models for studying whipping analysis of a ship. But in the report, it mentions that the 3D CKP models are more consistent and accurate, but the user for whipping is still conditioned by the limitations of the 2D slamming models. So from this point of view, I feel that the 3D effect quantification on the slamming models is very important in this subject. Next, I would like to make a review on the slamming analytical models and introduce the applications of them in my study. For this topic, a two-dimensional wedge impacting with water was initially studied by Van Karman in 1989. And this model neglected the wave surface elevation on this part. Later, Wagner developed this model by taking this into consideration. Both models are based on the flat disk approximation and the potential flow theory for ideal and incompressible liquid. The pressure on the vortex surface is calculated using Bernoulli's equation. After the initial studies, a lot of work has been done by other researchers to make improvements. In 2004, Professor Kropkin Alexander studied these models based on potential flow theory. The hydrodynamic pressure in the flow domain is given by the quasi-Lagrange integral. Were these expressions for the hydrodynamic pressure and the velocity potential? H means the penetration depth of the body into water, while F means the body shape. If we introduce the boundary condition on the body surface, we get this one as the pressure. Considering only the initial stage of the impact, we get a asymptotic solution for the velocity potential. By introducing this expression in the pressure formula, we can get this format of the pressure distribution, which is depending on space and time. In this equation, the function d was introduced to include the effect of the splash height of the water. With different assumption of the function, we have different analytical model. To improve the predictions, the higher order terms in Bernoulli equation were taken into account within the generalized Wagner model and Logvinovich models. The result of Professor Kropkin showed that the Logvinovich model corresponds better to the experimental data than the generalized Wagner model. And these models can be extended to different shape of structures and can be extended to also three-dimensional bodies. These models, with also the original Wagner model, have been applied in one study to study the local response of sample structure due to water impact. Next, we're going to see 5 examples of the application. The first example is the hydroelastic response of the wet deck slamming. The wet deck means the structure part connecting two hulls of a catamaran. Because of the flat geometry, which we have seen in the picture at the beginning of the presentation, very high slamming pressure can be generated. And for the part of the wet deck between two transverse stiffeners, an Euler beam with length of L corresponding to the distance between the two stiffeners can be a good approximation. And the hydrodynamic pressure on the bottom is estimated by using Wagner model. And the deflections of the plate at each time step was considered in the slamming load model, which means this solution is a fully coupled hydroelastic model. The second one is the dynamic response of elastic wedge subjected to slamming load. We also use a beam model, but here we applied the rigid body assumption when we predict the slamming load, and the modified Logvinovich model was applied. This case is considering the water impact between the front part of a slender ship with a width of a very big length. And next one is the wet deck slamming due to a single wave with very big wave height. The last case is the dynamic response of a horizontal composite plate subjected to slamming pressures. And for this study, we considered a sandwich plate with 3 layers, and for the skin layer and the core, we have different material properties. For the slamming load, we considered 2 different slamming pressure impulses. The first one is a triangle type, where we have a peak value and a loading period. The second type is exponential pressure. So for the exponential pressure, it was observed in our predictions on the slamming load for rigid bodies with small dead rise. And the triangle type was obtained in our study for flexible structures. Next, we are going to review this case briefly. In the first case, a asymptotic solution proposed by Professor Fortison was applied. So we consider the speed of the ship U and also compression force acting on the plate due to the connecting members on the hull. By considering these 2 parameters, we have this equation of motion for the hydrodynamic analysis of the beam, where EI is the bending stiffness per unit length, and Q is the longitudinal compression force per unit length. M is the mass of the plate per unit square. The elastic deflection is first expressed in terms of the joint normal modes by using this equation, where AN means the principal coordinates and phi are the eigenfunctions. By considering the symmetric beam, we have this type as the solution of the eigenfunctions. Consider the speed of the ship, we get this type of the velocity potential on the body which was proposed by Professor Fortinson, where the phi3 means the velocity potential due to forced heave with unit velocity, which is given by this formulation, where L is the length of the beam. Regarding the hydrodynamic pressure P, we considered the effect from the speed of the ship. And then if we introduce the velocity potential, we can get this type of the hydrodynamic pressure. Substituting the previous equation in the equation of motion for the beam, we can get this form for the equation of motion. Then by multiplying the eigenfunctions on both sides and make integrations on the verted surface of the beam, we can get this equation. The general form of the damped system is written as this, where m is the inertial coefficient, c is damping coefficient, and k is the stiffness coefficient. The three values of matrix can be calculated by using these equations. If we know the properties, the dimensions, boundary conditions of the system, we can get all the results. The experimental study carried out by Fortinson showed that the results associated with the first mode shape dominated in the response. So only the first mode was considered in our study. The table lists the plate properties and the parameters that we used in the calculation. To validate the model, we use a fully coupled ALE and a finite element method, which is implemented in the commercial software Elasticity. This is a fully coupled hydroelastic analysis. And we compared the predictions of the slamming pressure and also the deflections in the middle point of the beam. Here, these two figures compare the two pressures on two locations of the beam using the asymptotic analytical solution and the software Elasticity. We can see that for this case, with the 2.5 meters per second entry velocity, the commercial software provides very high initial peaks. However, we have very low initial values in the analytical prediction. Then for another case with a higher entry velocity, the Elasticity provides better agreement with the experiments. And for the same case, we compared the deflections in the middle points. And we can see that even there is very big differences between the predictions of the pressure. We get a better agreement on the deflection in the first half period. So this result is consistent with the conclusions presented by Dr. Simon Malencia. The peak value of the pressure doesn't affect the deflections on the structure's march. And for another case with a different boundary condition, the analytical solution provides also satisfactory agreement comparing to the fully coupled analysis. There are more results presented in the paper, and results are affected largely by the beam dimensions and the boundary conditions. The second case is about what impact on the elastic wedge. We use the similar approach, the Ona beam for the wedge and the model approach to get the deflections on the structure, but we didn't consider the structure deflection effects on the slamming pressure. So this is a dynamic analysis. It's different with the previous hydroelastic analysis. And similarly, we compared the results of the deflection in the middle point with the fully coupled analysis. Assume that the rotational inertia is small and the Gaussian equation of the motion for the beam is given by this equation. And similarly, we use the normal most to present the deflection first. And then we can get a differential equation for determining the principal coordinate AM. Here, in this equation, the right side is the generalized force, where the small p is the hydrodynamic pressure, which depends on space and time. We use the modified Lagrange model for the pressure. By using the Duhamel integration method, we can derive the response, where An0 is the initial deflection, which is 0, and this is the initial velocity of the plate. We considered this is the relative velocity between the plate with the wave. And to identify, to validate the case and to identify the hydroelastic effects on the model, we compared the deflections for different cases with different dead rise velocity and the plate thickness. As we mentioned before, the analytical model is a dynamic analysis, while the fully coupled ALE and the finite element solution is a hydroelastic analysis. So to compare the results predicted from these two solutions, we can investigate the hydroelasticity. Here is the results for the case with 10 degrees dead rise and for different plate thickness. And we can see that for these two cases, when we have a low or small plate thickness, the analytical results are very different from the fully coupled analysis. While when we have a large plate thickness, the agreement is much better. So in this study, we applied a ratio RF to present the hydroelasticity effect. The RF means the ratio of the loading period to the dry structure natural period. The value of less than 2 indicates that the hydroelasticity is important for the case. But if this value is higher than 2, we can consider the hydroelastic effect is small. Then we can apply the analytical model. So this statement was also proposed by Professor Fortinson, and our results are consistent with this statement because for these two cases we have very small RF, and here we have a value higher than 2. In this slide, there are the results for the case with a larger dead rise, the 30 degrees and 45 degrees, when the entry velocity is smaller, 1 meter per second. And for these cases, we can see the analytical models provide satisfactory results in the time story of the response at the middle point, compared with the fully coupled ALE and the finite element analysis with also a boundary element solution. To study more about the hydroelasticity, we compared the maximum deflections for the wedge with different impact velocities and different plate thickness. This table provides all the ratio RF for these cases. And we can see that when the velocity is small, all the values are higher than 2. And when the velocity is increasing, these values are decreasing. If the plate thickness are higher, the values are still large. But for the case with a very high entry velocity and the plate thickness are very small, we have very small values. And these cases have very high have very high hydroelastic effects on the results. And these results are also consistent with the present study. So in these figures, the horizontal axis is the entry velocity. The horizontal axis are the maximum deflections from different methods. And the red one is from the present simplified analytical analysis. When the velocity is 1, all the simplified values are in good agreement with the fully coupled analysis. But when the velocity is higher, the deviation is increasing a lot. In this slide, there are some pictures from the fully coupled ALE and finite element analysis. We can see that during the word entry process, we have deflections. So it is a fully coupled analysis. To see the differences between the applications of different slamming models, we also applied the generalized Wagner model and the original Wagner model in our simplified analysis. And we compared the deflections from these different slamming models. And we can see that with different slamming model, we predict different structural responses. It means that the accuracy of the prediction on structural response is affected by the accuracy of the slamming load. The present study indicates that the simplified method gives satisfactory predictions of the deflection on the elastic wedge when the hydroelastic effect is not significant, and it is validated for the cases with larger dead rise, low entry velocity, and high plate thickness. It is also interesting to see the differences between the simplified model and the fully coupled analysis. So for the simplified method, it is easily derived and solved based on potential flow. The coupled ALE and finite element method is very sensitive to meshes and time step. The numerical uncertainty is due to the discretization and the experience of the users are also difficult to be identified. But this solver can simulate the compressible and viscous flow. The simplified method can be applied for the wedge with arbitrary dead rise angle and constant velocity. And of course, it is possible to extend the model to more geometries with different boundary conditions. But the numerical analysis can be used for an arbitrary geometry with arbitrary boundary condition and velocities. However, from the CPU point of view, the difference is very high. So we consider the same case for the wedge with 30 degrees dead rise. We can get the results within 2 minutes in the simplified model, but we need 24 hours in one 2-dimensional simulation, which is very high. And if we study a 3-dimensional case, we may need 1 week. The next case is the impacting between a slender ship with a very big wave. And the solution is very similar to the previous one, so I will review very fast the case. Here it is the approximated model for the problem. We consider the shape is Euler beam, and the beta is the relative angle between the wave surface with the beam. The V is the relative vertical velocity between the structure with the water. So we apply also the Euler beam equation of motion. And then we express the deflections using the normal modes. And finally, we get this equation for determining the principal coordinate. And in this equation, this P is also the hydrodynamic pressure on the rigid body. It is still the rigid assumption model. We use the boundary equation to derive the hydrodynamic pressure. The analysis was validated by using the direct finite element analysis in ANSYS. And we consider different number of the normal modes in the analysis. We can see very good agreement was achieved. There are also different results for the maximum deflections for the beam if we consider different different relative angle between the wave with the cylinder shape and also different relative velocities. The case 4 is the vertex slamming due to a single wave impact. And we use the equation of motion for an isotropic plate, which is given by equation 13. The D means the plate flexural rigidity having this expression, and the M is the mass per unit area of the plate, where this is hydrodynamic pressure acting on the plate due to the single wave. And the normal modes of the simply supported plate can be written as equation 14, where we have the following natural frequencies. Then by using the expansion theorem, we can express the transverse displacement on the plate by equation 16. Here Q is the modal coordinates. To get the modal coordinates, we need to get the generalized or the modal forces. The modal forces contains one expression for the pressure. And this pressure was obtained by considering a simplified wave profile. The wave profile is given by equation 19. Then we can get a vertical length on the plate. By using the linear term in the boundary equation, we can derive the hydrodynamic pressure as given by equation 22. So we apply this equation in the equation 18 to get the modal force, and then we get the modal coordinates. Then we can finally generate the structure deflection on the plate. The results were also validated by using the direct finite element dynamic analysis, which have good agreement. And the first natural mode dominates in the response. Recently, we have been studying the dynamic response of composite plates subjected to slamming pressure, because the composite material is becoming more and more attractive because it is lighter and more flexible. The hydroelastic is more important for this type of the analysis. This is a cross-section of a sandwich plate, and for different layer, there are different material properties. In our study, we consider 3 layers: the skin layer and the core with PVC foam. And here, this table shows the material properties for the skin layer, while this one shows the properties for the core. With these two tables, we can derive equivalent isotropic plate by using the rules from BV, and where we have the following material properties. If we use these material properties, we can get the response of the plate using the isotropic plate equation of motion, which is given here. Considering the simply supported boundary condition, we have these conditions, where we have the eigenvalues. And the equation is solved by considering the particular solution and the homogeneous solution, where the hydrodynamic pressure on the plate was proposed by two different slamming impulses. One is exponential, the other is triangle type. The two proposed slamming pressure are shown in this figure. And in this study, we would like to study the effect of the three parameters, Pm, which is the peak value on the pressure, and Td1, Td2, which are the loading period on the pressure on the slamming-induced response. So we applied different values for different cases. With the three values, we have the two expressions for the exponential and the triangle slamming impulses. By applying the Navier's method, this load can be expressed in the form of a double trigonometric series in the following two equations. By applying these two equations in the previous equation of motion, we can get the structure deflections at each time step and at each location of the plate. Firstly, we validated the analysis using the numerical analysis. The numerical analysis was derived in Fpso as well. And here it is the comparison of the deflection in the middle point of the plate when we apply the exponential impulse with this value for the peak pressure and this value as the loading period. The T11 means the first natural period of the plate itself. And in the numerical analysis, we applied the same material properties, the same boundary condition, and the dimensions. Also, we applied exactly the same exponential impulse. We can see that the agreement is very well because the deviation is only around 1.69%. Here is the comparison for the case with a triangle slamming impulse. And a little bit high deviation was observed, but it is still considered satisfactory. Then we studied the influence of the different parameters. Here there are examples for the results of TD1. So for the four cases, we apply the same peak value on the pressure, 25 kPa. And for each sub-figure, we use the same TD2, but with different TD1. There are some interesting results. For example, we can see that for all the cases, if we use TD1 equals to T11 and the double of T11, the amplitudes are equal. And when the TD1 is 1/2 of the first dry natural period of the plate, the peak oscillation amplitude is always high. And then when the TD1 and TD1 is equals to T11 and double T11. For these two cases, we don't have the free variation phase. Here is one example for the study on influence of TD2. For the three cases, we applied the same amplitude and pressure and same TD1. But we can see that for each case, for all the cases, TD1 has no effect on the maximum amplitude. They are always the same. And for these two cases, when TD1 equals to T11 and double T11, the peak values are the same. But if TD1 is 1/2 of T11, this value is higher compared with these two. Here is one example for the study on influence of TD2 for the exponential Slamming impulse. And we can see that even we use the same amplitude on the peak pressure, we get different amplitude on the deflections. If the TD1 is higher, we get higher amplitude. So the loading period is very important in the analysis of structure response. In order to identify the hydroelastic effect on the composite plate, we also simulate the watt entry of the same plate using the fully coupled ALE and the finite element method. And here is the result of pressure and the deflection. In this figure, this curve is the prediction of the average pressure from the fully coupled analysis. We can see that it is more fitting with the triangle type. So we proposed this triangle where we use the peak value on the from the FSI analysis as the PM in the model, and we use the TD1 as this point to this point, and we use this as the TD2. So if we apply this triangle slamming impulse in the analytical model, we get this one as the deflection in the middle point, while the purple curve is from the fully coupled ALE and finite element method. We can see that this analytical model over-predicts the deflection. Okay, it means there is very significant hydroelastic effect. So in order to get consistent deflections, we modify a little bit on the triangle slamming pressure impulse by using a smaller PM. So with this triangle model, we get a very similar deflection. So in this study, we proposed two slamming pressure impulses in the analytical model for solving the same problem. The model can be easily adapted for other materials and other pressure distribution. It allows to highlight the influence of different parameters in the analytical model. By comparing with the fully coupled analysis, we can see that the triangle slamming impulse is suitable for the modeling of pressure distribution during the water impact of the composite plate. And this comparison also demonstrates the high hydroelastic effects on the case. So this is what I want to present today. To conclude my presentation, I would like to say that the analytical models are very useful and robust for some practical cases if they can be approximated properly. Thank you very much.
Thank you, Dr. Shan. Thank you for your presentation. We have time for questions and for comments. So everybody invited, so you can raise your hand to ask, say, permission to speak, or just you can unmute your microphone and to say something, or you can write in chat. So there are several options. So it's up to you how you want to respond to this presentation. Yes, please. Any others? Anything? Yeah. While we wait for questions from others, may I ask you to show case 3 and normal mode?
Okay. Full mode or not?
Normal modes, formula for normal modes, case 3.
Okay.
Is it case 3?
Here?
Yeah, okay. So, yes, so equation 3. Can you see equation 3? In equation 3, mass m of m depends on x. Rigidity.
You mean here?
No. Can you hear me?
Yes, I
Equation 3. Equation 3. Not 1. Equation, yes. Just stay on this slide. Do not move it.
Okay.
And then that in equation 3, m of x, m depends on x. Rigidity depends on x, right?
Yes.
In this formula.
Yes.
So how you manage to get 4?
For this case, I considered the uniform beam. So M and EI are consistent. But if we study a real ship, we need to consider the mass distribution and rigidity distribution. And generally, yeah, please.
So equation 4 is for m and rigidity, mass and rigidity constant. Is it right?
Yes. Yes.
Okay, where m and I are constant. Okay, for the beam. Yeah. It's just written above between 3 and 4. I didn't pay attention to that. Okay. And any other questions? Just the if not. Yeah, then can you go, please go to the beginning, and there is a slide with ISSC 2018 table. Yeah, this table. Could you explain me about this committee, what they are doing, and is it important for engineers or for researchers, or it's just a recommendation by this committee, or how to understand such tables from the committee? And what's altogether ISSC? What's that?
ISSC is the International Ship and Offshore Structure Congress. So it consists of 16 standard committee, and for different committee, they are reviewing the studies in the previous 3 or 4 years in different fields. And for here, this is 2.2. The 2.2 committee is regarding dynamic response, ship structures and offshore structures. So every 3 years, we summarize the previous study and the improvement in different subjects. This is the... Now I am in this committee for the 2022. And I think Dr. Simon Valencia or in this committee.
Oh, okay, okay. And how the conclusions of this committee are important, or they must be taken into account by researcher, or just its recommendation? Could you explain the kind of power of that committee?
I think I kind of summarized the report here. So here they mentioned that the hydroelastic model involves the three models, and the differences between the potential flow method with the CFD method are how can I say apparent. For the potential flow theory based method, they are useful for the cases when we want to study springing response, and for the cases in heading waves. But if we use these models in, for example, beam waves, and for the structure with very big torsional vibration, and the result is not so accurate. And also this method is, as I mentioned here, it is limited by the 2D slamming model, because we always apply the Wagner model or the momentum theory or the Lovinovich model to get the section force due to slamming. But the section force is only two-dimensional. In the slamming of the ship, in addition to the transverse direction, the fluid is also spreading in the three-dimensional, in the longitudinal direction. So, in my opinion, the 3D slamming model is also important to improve these models.
Yeah.
And now I'm also writing the report for the next, for 2022 report. And I found that this potential flow theory is not, has not been developed with very high progress. More analysis is performed using the coupled CFD and finite element method. But this is very difficult and time consuming. We cannot use it for all the cases because the analysis is different case to case, and different people have different results due to the experience of the user. So I think this is very difficult, and the potential flow based solution is still very useful and practical.
Okay. I have could be the very last question, but I believe you can speak a lot about commenting this question. You mentioned slamming with respect to ships and offshore structure. And the offshore wind turbines is also offshore structure, right? Yes. Or offshore solar panels, floating solar panels also structure. So there is the applications and place for slamming of violent flows studies in green energy aspect. So could you please comment what the place of that, say, slamming, wave loads, how they are important for wind energy, for solar panels, floating solar panels, and other aspects of the of that green energy, offshore green energy.
So for the offshore structures, for example, the wind turbine problem, there are also some study about the wave impact on the platform which supports the wind turbine. But I think the analytical models are very difficult to be applied because they are more about the breaking wave impact. But for breaking wave impact, we cannot use potential flow. It is we need to use the real flow theory. So most of the study are performed using CFD solution, and they are considering the wave is coming, the instant wave coming, and the impact with the platforms. There are also some study about the bottom slamming. So if this is the one part of the platform, and the wave is coming and impact with the plate. So this is very similar to what I mentioned in the wet deck slamming for catamaran. It's similar. So maybe for this case, we can use analytical method. But for the breaking wave impact is difficult.
Okay, but how about floating solar panels? Because I understand they are very close to the surface, placed, so it's there are no wet deck for solar panels. But still, is the waves and breaking waves can be damaging for the floating solar panels?
For the you mean the floating structures? So
floating
for the
solar panels.
Sorry?
Floating solar panels.
For the floating structures, they are also using this type of the hydroelastic model. But in this case, we cannot use the strip theory, because the strip theory is only valid for slender structure. So for the floating structure, we can only use 3D method. For example, 3D boundary element solution. If we want to use potential flow.
Yeah. What's the most important for practice for industry to know about the slamming? Is it pressures, stresses, or I don't know, lifetime of the structure? What's the final kind of results of interest for the industry?
So this is, in my opinion, okay.
Yeah,
there are a lot of studies regarding slamming, the slamming pressure prediction and the response analysis and the hydroelastic models. But I think the final objective of this study is to include the slamming, the nonlinear slamming effect on the design load of ship. Because when we design a ship, we need to follow some rules, and there are some design loads. For different load, for example, for different loads, we have different dimensions or the scattering on the plate. So I think it is very important to find a way to include this effect in the rules of classified society. And I think the most important one is for example, the ultimate strength. The ultimate strength of the structure due to the load, including slamming. It's not only slamming, but including the effect of slamming.
Okay, then sorry. Last question. You mentioned the rules or guidelines from the certification society. As I understand, and is it right that that rules, they are formulas? They are just written that the loads is like that, like that, like that, depending on the environmental conditions like wave height, frequency, or wave spectrum, or other things. So there, in the rules, there are no CFD. Is it right? So the CFD is used on the way to arrive to these analytical formulas. Is it right?
Yes. So there are a lot of
empirical
formulations.
Yes.
In the rules, and these empirical formulations can be obtained by using experiments the safety analysis and also analytical analysis.
Yeah, yeah. Okay, but finally, this is the formula, and kind of certain values, how they depend, like loads, how they depend on other things, like environmental conditions. Yeah. So the final result is formula. This is what the industry. Okay, formula, and also with the conditions how to use this formula. Right? Because for one speed, the formula can be in one form, and for another speed of the ship, say, the formula could be different. Okay, okay. So, yeah, interesting. So this means that we are doing research, but finally, almost nothing is important except of the kind of the very concentrated knowledge about the formula, and that is the formula. It's not the pictures, it's not the colored pictures, it's not the graphs. Oh, could be graphs, but the for some dependencies, but mainly it's formula. That is interesting. Yeah, something it's good to know what finally is needed. Right. So it's not but the kind of knowledge about the what depends on what and in which way. So yeah, any other questions, please? Okay, not many. Then thank you very much indeed. It was very good to know the opinion and what has been done in this field in terms of the shapes and the committee you are in now, and offshore structures and how it can be applied to the green energy as well. Thank you very much. And there are many thanks I'm receiving for your very nice talk. I believe you also can see the chat.
Thank you very much.
Thank you for your presentation, and thank you for all the participants. Then I do not close the section, the meeting, but I should switch off my microphone and camera, and because I need time to upload, no, not to upload, to download the video, and after that I will send this video to all participants of this seminar, and also to the people who could not attend your nice presentation, and they could watch your presentation in their time convenient for them. Okay, so thank you very much indeed, and bye-bye. We are closing this seminar. Thank you. Please do not forget that next week we have a presentation, very interesting and fundamental presentation from Professor Zillman from Tel Aviv University. The same time, please come. The invitation will be sent to you. Bye-bye. Bye.
Okay, bye-bye. Have a nice afternoon.